Logistics for this week. Problem set 5 is due tomorrow at 2 p.m. in the basement of Campbell. It may say 4 p.m. on top of it. I'll get it at 4. Sorry for the typo, so for those who didn't make it, we don't have too much confusion. But for the future, we're going to shoot for 2 p.m. There is talc tonight, as usual. Professor Bloom will be back on Thursday, so we won't have office hours today. If you really want to meet with him, email him and try and set up an office hours. But you're also welcome to come to my office hours today, 2:30 to 3:30 in 753A Campbell. For those of you who don't know, that's on the roof where the elevator doesn't go. So you've got to go up to the 6th floor and take another flight up if you want to come find me. Any questions about logistics before we move on? He's away giving a talk. At a conference, yeah. Got a last-minute invite. I don't actually know. It's a good question. But he will be back on Thursday, and we'll be back for lecture. All right, so last time we talked about a few things. We talked about the stages of the interstellar medium and put up this simple table talking about 3 stages, plotting or showing temperature and density, or number density in terms of particles per cubic centimeter, of the hot, the warm, and the cool phase. And we noticed that this number NT was about the same for all of them. And we said that represented pressure equilibrium. That wasn't terribly clear. We have the physicist's version of the ideal gas law. Let's get this right. Where pressure times volume was the total number of particles times Boltzmann's constant and temperature. So if we divide through by volume, the pressure is little nkt, k is a constant. So this really is sort of a unitless, or well, not unitless, but pressure not in the right units. Multiply by a constant k to get pressure. But so all these phases are sort of in pressure equilibrium, which you'd expect. If there were different phases of the ISM exerting more pressure on other phases of the ISM, that it wouldn't be stable, and some of those regions would collapse and others would expand. And so it's sort of in a steady state for the interstellar medium. But of course, we showed that authoritative slide from Wikipedia demonstrating that this was a pretty simple picture. It had a lot more phases of the ISM and a lot more details as far as these numbers go. But these are reasonable, typical numbers. And then we also talked about various emission and absorption processes in the ISM. I mentioned 21 centimeter emission. The spin flip transition of neutral hydrogen is a tool to detect neutral hydrogen in our galaxy and in other galaxies, which we'll get to later. We talked about the carbon monoxide molecule as a tracer of various molecular gases, but CO is the most easily detectable. So we use its measurements to convert to other molecular gas measurements. And finally, we talked about Bremsstrahlung radiation, this German braking radiation. Those of you ever go to a talk or see a paper that refers to something called free radiation, that's the same thing. This is the radiation where you have a free electron being accelerated by a free proton due to their Coulomb forces. Accelerating charges emit radiation, so some people call it free. So they don't have to use the German. Any questions about what we talked about last week? Yes. So it could be other ions in terms of the nucleus, but as far as the force of acceleration, the proton is so much more massive than the electron that it basically stays still, and we have the electron breaking around it. And so other ions are even heavier, and they would stay even more still. So it really is the electron that's doing the radiation. All right. So we have one more thing we want to talk about with regard to the ISM today. We'll see how well I do here. I have terrible spatial reasoning skills, so I might make terrible use of these boards. But we wanted to show a little derivation talking about H2 regions. And specifically, what I'm about to do is the derivation of what we call the Stromgren sphere. named after the person who first did this sort of calculation in the 30s. So H2 regions, if you recall, this is H Roman numeral 2 is ionized hydrogen. H1, Roman numeral 1, is unionized hydrogen. So if we have a setup, we're in the middle, we have a bright star, say an O star. For those of you who don't know the stellar names, this is sort of the brightest kind of star. And it's pumping out a lot of ultraviolet photons. These very large, very hot stars emit a lot of ultraviolet. And so if we have E photon greater than 13.6 electron volts, that's enough to ionize hydrogen. So we sort of imagine a bubble of H2 around the O star, and then neutral hydrogen outside of this bubble, as the star is basically blowing ionizing photons isotropically into this medium, ionizing this hydrogen. And we want to know what's the characteristic size of these bubbles. So we'll call this RS, or the Stromgren radius. And basically, again, we want to find a steady state solution. We want to balance equilibrium. Specifically, the number of ionizations equal to the number of recombinations. So we're in a steady state situation where for every hydrogen atom that gets ionized, there's another hydrogen atom that is recombining, becoming a neutral hydrogen atom again. And we know these recombinations take place. If you remember, we talked about fluorescence, where an electron is recaptured by an atom and falls down these energy levels, emitting a lot of photons. And we'll see some pictures of H2 regions. They're characteristically red. That's the hydrogen alpha recombination transition falling from 3 to 2. So these all have a characteristic red color. But so let's make this a little more quantitative and do sort of a per time, per volume calculation. So this is the basic situation we want to set up. The number of ionizations per second per cubic meter is going to equal the number of recombinations. That will be a steady state situation. Yes?
Wait, so why do they have to be equal?
So if this weren't equal, for example, if the number of ionizations were greater than the number of recombinations, then we'd imagine this bubble would be growing. And we're looking for sort of the steady state situation where eventually it's going to stop growing. All these photons will be used up, and there won't be any more to get further than this radius to ionize the outside H1. So yeah, for a period of time, once the O star forms, it will blow this bubble, and this bubble will grow and grow and grow until eventually we reach this steady state situation. We basically run out of photons. For every photon that gets used up, we get a recombination. So let's evaluate both sides of this equation. I want to start with the right-hand side. So we want to know the number of recombinations per second per cubic meter. So let me write out some faux chemistry equations for these transitions. An ionization is a photon plus a hydrogen atom turns into ionized hydrogen and electron. Anyone know another name for ionized hydrogen? Right. This is just a proton. So we're hitting a hydrogen atom with a photon, turning it into a free proton and a free electron. And so the other side is the exact opposite equation. And again, these are the photons we see in fluorescence, the photons that are emitted as the electron cascades back down. So to solve for the right-hand side, we need to know basically how often does a free electron hit a free proton in this ionized gas. And so we'll set up sort of a optical depth type problem where we have here our electron moving at some velocity v, and I've drawn it with some cross-section, sigma. Make that bigger. Sorry, the right-hand side of this equation. So then I'll come back and do LHS. So we've got an electron moving with some velocity, and I've got some cross-section, that is, an area. And we'll come back to exactly what that area is in a second. But I'm imagining it moving down this sort of tube of length, we'll call it v delta t. I suppose I should turn my cell phone off while using this microphone, is what that noise is telling me. And in this tube, we've got a bunch of protons. So we want to know, for this situation, how often does an electron hit a proton? And so we can set up the volume of this tube. Well, it's the length, v delta t, times sigma, this cross-sectional area. So cross-section is sort of, you can imagine it as the area, or the distance the electron needs to be from the proton for this recombination to happen. So geometrically, cross-sections are fairly straightforward. If we have two balls moving at each other, the cross-section is the geometric area of those balls. If they're further apart than that, then they pass right by each other. But if they're closer, then they hit each other. Actually coming up with a value for this cross-section is not trivial. But we'll think about that in a minute. I'm just going to leave it as sigma for now. And so we want to know the number of protons that this electron hits. Let's start with that. So if I call this tube with a density of protons np, well then, for every volume of this tube, I hit np, which is a number density per cubic centimeter, protons. I hit all the protons in this tube. So it's np times the volume. And let me move over here because I have not mastered writing at the bottom of a board yet. We can set this to a rate. Number of protons hit per second. We have a delta t in there, so we just set delta t to be 1 second. The length the electron would travel in there and cancel that out. So this is np v sigma. And finally, we want what we had here, the number of recombinations per second per meter cubed. So we need to know the number of electrons per meter cubed. That will give us the total number of collisions in this entire unit volume. Well, the number of electrons per meter cubed is simply the number density of electrons. So this is our final expression, that we have Ne, Np, times the velocity of the electrons times this cross-section. And I'll say it's typical, well, first point I want to make, for H2, ionized hydrogen, how are Ne and Np related? They're equal. So we're going to assume this is pure hydrogen, and we're going to set these two equal and call this the number of hydrogen atoms squared times V sigma. And I'll say, you'll often see this definition, sigma times V, we'll call alpha. Is the recombination coefficient. And so we have a final expression for the right-hand side. NH squared alpha. Yes?
I missed the step where we introduced the number density of electrons. How do we get that?
So this was the total number of protons hit by this one electron moving through this tube. We now want to know per unit volume what is the total number of protons hit? Well, it's the number hit by one electron times the number of electrons in that volume, which is given by the number density. Yes?
Why don't the protons also have a sigma?
So the sigma is going to depend on the electrons and the protons. It's the overall cross-section for an electron to hit a proton. That's a good question. Yeah, I haven't really talked too much about sigma, as I said. We'll come back to that. But here is our, we'll leave this as is for now. And then we want to go and evaluate the left-hand side of this equation. So this one, let's go over here. Can people see if I'm over here? Okay. So this was the number of recombinations. And so I made the assumption that every time an electron hits a proton, with hit defined by this cross-section, we get a recombination. So I'm going to make a similar assumption here. I want the number of ionizations. I'm going to approximate the number of ionizations as the number of ionizing photons put out by this O star, which is photons with energy greater than 13.6 eV. So we're saying every photon with energy greater than 13.6 electron volts is absorbed by a neutral hydrogen atom and ionizes it. Yes?
How good of an approximation is that?
Not a bad one for an O star. So if the star were emitting X-rays or gamma rays, then they could travel right out of this region without interacting. But O stars sort of are ultraviolet emitters. They don't really emit higher energy photons than that. And the cross-section for a hydrogen atom absorbing an ultraviolet photon is very, very big. So it's not a bad assumption. Okay, and so we want to do the same thing we did here, go from a total number to a number per second per volume. So let's call we'll just come up with a name for the number of ionizing photons per second for now. We'll call that capital N. And then we need finally, to get these things looking the same way, the number of ionizing photons per second per meter cubed. So this is the number of ionizing photons per second put out by the entire star. So to get the average photon per cubic meter in this entire H2 region, we need to divide by the volume of that H2 region. So this is N over V, where V is the volume of the H2 region, 4/3 pi rs cubed. And so that is our equation for the left-hand side. So let me go back over here, and we'll set these two equal. Right? We said we want balanced, so we're going to set them equal. I can't see too well over there. So my right-hand side was NH squared alpha, and my left-hand side was capital N over 4/3 pi rs cubed. We set these equal. What we wanted was the typical size of this, so we solved for rs. A bit of algebra, but not too bad. Do some of that algebra if anyone's curious, but it's really just rearranging those terms. So we have the Stromgren radius, the typical size of an H2 region, is given by a fairly simple formula that depends really on three things: the density of hydrogen atoms in the region, the number of ionizing photons put out by the star, and then this recombination coefficient alpha. So it's a nice formula, but let's actually work out how to get some of the numbers here. So let's evaluate this. How do we get n, capital N, little n, and alpha? So what's the right way to get the number of ionizing photons put out by a star? Question first? Oh, yeah. How would you get the number of ionizing photons? So we're saying that n is the luminosity of the star divided by energy of the photons, h nu. So we want all the photons greater than 13.6 eV. So I'm actually going to come back to this in a second and use this as an approximation. But to actually get the right answer, we need to take this. The luminosity is going to be a function of frequency. And then we need to integrate from 13.6 eV to infinity over energy. So the total number of photons greater than 13.6 eV, we need to take into account the frequency dependence of the luminosity. As you know, stars are roughly black bodies, so it emits different flux at different frequency. But as you suggested, a good approximation, sort of already used it once, is that black bodies are peaked. They have, we know from Wien's law, a characteristic temperature, which corresponds to a characteristic wavelength or frequency at which they emit. So we're going to approximate this as L star over h nu typical. Assume that all the luminosity of the star is coming out at basically the peak of the black body. It's not a terrible assumption, and it's a lot easier than doing an integral when we don't have an analytic form for the luminosity of a star, if you have to take into account all the spectral lines it has and things like that. So that's our approximation for capital N. Let's see. I don't want to erase this quite yet. Yeah, I'm calling it the typical wavelength. You can call it the peak frequency. It's not a terribly well-defined quantity, but yeah, the best way to get it is to know the surface temperature and to use Wien's law. So let me actually move this over here, so I don't have to erase that board just yet. And let's get some of these other numbers. We still have alpha, and we still have little n. So let's do alpha next. So we said alpha, and I'm going back on my definition, was sigma v, the cross-section, times the velocity of the electrons. So I'll do the velocity here. Let's assume that they're in thermal equilibrium. So we can set 1/2 mev squared equal 3/2 kt and solve for v. Which, if we plug in numbers, they're moving at about 6 times 10 to the 5 meters per second for a 10,000 degree H2 region, which is a typical temperature. I forgot to say, let's plug in some numbers here too. So this is, in our case, an O star. So I'll give you some numbers for an O star. It's about 10 to the 5 times as bright as the sun. H is H. I'll say this is 3 times 10 to the 31 watts. And nu typical, if we went through Wien's law and calculated it winds up being about 10 to the 14 hertz. That's sort of where the black body for an O star would peak. And if we plug in all these numbers, we have 10 to the 31 over 10 to the minus 34 over 10 to the 14. Get about 10 to the 50 photons per second. And I'll box this for V at 6 times 10 to the 5 meters per second. So we've got N, we've got half of alpha, and we need NH. So now we need to think about sigma. So I'm going to pause for a second and ask you guys to turn to your neighbors and talk about this for a minute. What are sort of an upper bound and a lower bound for the cross section, if you can come up with these numbers? Sort of, this is the area. You can think of the cross section as the radius squared. So the distance the electron has to pass by the proton for them to recombine. Now, it's a hard number to come up with, but can you sort of put some reasonable bounds on it? It's got to be bigger than something, and it's got to be smaller than something. Just
Bigger than the radius of the proton. Yeah, definitely. And then upper bound is like the escape velocity from the potential. Yeah. So it's like 13.6 converted into what?
So is that a lower bound?
all right.
What is the cylinder's radius?
Yeah, well, after, like, what is it?
But if you like, just see the Coulomb interaction.
I think, like, as it becomes larger, it goes, like, inversely.
All right, so I think people are quieting down or changing topic. So who came up with an upper bound? What's a good guess? Sigma's bigger, has to be bigger than what? So right, we'll call this RP squared, because remember, sigma is an area. So we're saying, we have an electron heading at a proton. It doesn't make any sense if it comes closer than the radius of a proton and still doesn't hit the proton. That wouldn't make sense. So the radius of a proton is about 10 to the minus 16 meters. So that's small. So now the harder one. Did anyone come up with an upper bound for sigma? Do you have a guess?
Yeah, so negative 13.6 eV is the energy you need to ionize it, and so if you convert that into like a distance using Coulomb's law or something.
So I think that actually works out to be right. The way I thought of this, there is a characteristic size of the hydrogen atom, which it's called the Bohr radius. So the Bohr radius is sort of a combination of fundamental constants that uses Coulomb's law to get basically the size of an electron cloud around a hydrogen atom. So the way I thought of saying this claim was, if we have a hydrogen atom, it's got a proton in the middle and a big electron cloud outside of it. If the electron passes inside that electron cloud, maybe it probably should be captured. Whereas if it passes outside the typical size of that electron cloud, then it doesn't make that much sense for it to form hydrogen. So the Bohr radius is about 10 to the minus 10 meters. And so sigma is this squared. Well, we've got sigma within 12 orders of magnitude. It's bigger than 10 to the minus 20, and it's bigger than 10 to the minus 32, and is smaller than 10 to the minus 20. That's actually not bad. So if we go through and get the real number for sigma, it's about 10 to the minus 24 meters squared. So to do this properly, it's not really a quantum mechanical effect. You can do this classically, but you've got to take into account the Coulomb interaction, that as the electron is coming towards the proton, they're attracted to each other, and it's going to kind of bend towards it. So it's a dynamics problem that you have to work out. And you get a number around 10 to the minus 24. So if we combine these, then we have alpha is about 10 to the minus 19. And what are the units of alpha? Yeah, whatever that is, meters cubed per second. That is our recombination coefficient. And finally, to actually plug some numbers into here, we need little nh. So forgive me if I come over here. Well, if we looked at that ISM table that I erased, we said for the warm ISM, it's about 10 to the 4 Kelvin, and had a number density of 100 per cubic centimeter. So if we want to convert this into cubic meters, we need to be a little careful. And remember to cube our conversion factor. But we get that NH is about 10 to the 8 hydrogen atoms per cubic meter in a typical H2 region, based on that ISM data. So now we've got everything we need to plug into the Stromgren sphere. We have a recombination coefficient, we have a number density of hydrogen atoms, and we have the number of photons, ionizing photons, coming out from the O star. And so if we plug in, these ionized bubbles are of order 5 to 10 parsecs in scale, and sort of pretty ubiquitous. So let me see if I can figure out how to put this projector down and show you some photos of these things. And if people need another second to copy that down. How do I turn the lights off up here? So here's probably a familiar picture. This was a planetary nebula where the white dwarf inside has ionized this bubble around it. So this is a similar concept. Instead of an O star, we just have a very, very hot white dwarf. So this actually is a little bit smaller. But there's our schematic picture of a star pumping out these photons, blowing this bubble in a cloud of H1. And then there's a good picture of an H2 region. So the interior cavity has basically been cleared out in these physical systems, that the winds from the star, that we'll talk about later, have blown all the gas out. But then this ionized gas around them has a characteristic red color, which comes from the fluorescence of, as I said, the Balmer H-alpha transition, n equals 3 to 2. Is very, very red. So these things have a very characteristic red color. And when we look at other galaxies, when we get to later in the course, we'll see evidence for star formation are these big red blobs everywhere, these H2 regions, because O stars are really not very long-lived. So to have an H2 region, you need to have a recent burst of star formation that produce some very big, massive stars. I think that is that. Any questions about pretty much the ISM before we move on to the next topic? Okay, so let's put that up. Yes, question. So it's typical temperature of the ionized gas. So it heats up from the ionizing photons.
Sorry, is that a chicken in a can?
Yes, that is a chicken in a can. But yeah, so 10 to the 4 is a typical temperature of an H2 region, which if you remember from the table, we called the warm ISM. So there's actually a hotter component, but it's much, much less dense. And so that's a different phase. You need this somewhat dense gas, because this gas stars formed out of originally, and then is blowing this bubble into. So if it wasn't very dense to begin with, it wouldn't have formed stars to begin with. So the H2 is typical of the warm ISM. All right, so we're going to move on to bigger and grander things. Talk about the structure of the Milky Way galaxy as a whole. We've talked about the interstellar medium, stuff between stars. You did stars in 7A for those of you who took it. So let's start putting all these pieces together and take a look at how our galaxy looks as a whole. So let's... So the way I'm going to go about this is to cheat and give you the answer first. So I think this is, in some ways, less interesting than to just throw a bunch of facts at you, because there's a lot of size scales, a lot of facts, and it's kind of hard to remember all of them. But when we actually start delving into the question of how do we know all this, which I'll come to in just a few minutes, I think it's better to have a context of what I mean when I say these are found in the disk versus these are found in the bulge and things like that. So, and these are numbers that are good to know. You're not going to have them memorized necessarily for this course, but as you go on, some of these size scales are really useful to have in the back of your head. But so that said, let me draw the Milky Way, and this will be hopefully not too embarrassing for me. So that's my initial sketch of the Milky Way. It's a little lopsided. The actual galaxy is probably symmetrical. So there's a central point we talked about earlier in the class of Sagittarius A star, the 10 to the 6 solar mass black hole, lies right at the center. And just, well, let's say we've got the sun. If we define sort of a radius from the center of the galaxy, the sun is here, and this R about 8 kiloparsecs away. So it's 8,000 parsecs from the center of the galaxy. And again, how do we know that the sun is there was a major debate, and maybe we'll get to that at the end of class today, or not on Thursday. If not, we'll get to it on Thursday. The sun and pretty much all the other things out in the galaxy rotate around at a speed of 220 kilometers a second, give or take. And so for making measurements of other stars, we often define a local standard of rest. The exact definition is a little bit tricky, but basically it's subtracting out this 220 kilometers a second from the sun relative to the galaxy, so we can then measure how other stars are moving relative to us. Getting your velocity standards right is actually really, really difficult, so we won't go into that too much. But so, in case my drawing isn't clear, the Milky Way has a disk. And a bulge. Those are sort of the two main components of it, this flat disk and the sort of big bulge in the middle. The radius of the disk, and this is in stars, so how far out do we see stars? This is of order 25 kiloparsecs. So the sun, as far as is maybe a third of the way out from the center of the galaxy towards these outer edges of the disk, which is not how I've drawn it, but sort of the number of stars is falling off down here. And then I should say, as I draw off the edges of the board, surrounding all of this, basically off the disk, is what we call the halo of the galaxy. So sort of imagine this embedded in a larger sphere, and that sphere is the halo. So I should say one or two more facts about this before I actually start talking about some of the components we find in the galaxy and how we know how these things are there. In the disk itself, we find the disk is the site of pretty much all the star formation in the Milky Way. There are new stars here. There is plenty of gas. There's plenty of dust. We've shown you pictures of the dust. As you look towards the center of the Milky Way, you see this big, thick dust obscuration lane. And that's all in the disk. Whereas the halo is relatively gas and dust free. It's comprised of old stars, and as we'll come back to, if not this week, next week, dark matter is all in the halo. And the bulge has old stars, new stars. It's kind of a hodgepodge. So that's the picture we wanted to put up. Just so keep this in the back of your mind as we talk about, when I say this object lives in the disk, this is what I mean, as opposed to the halo, as opposed to the bulge. So. And I have some slides showing much better pictures of that, so if my artistically challenged drawing is confusing. Yes, question? So that is a very, very interesting question. When we actually come to measuring speed as a function of distance, the results are very, very surprising.
So it's not like an angular speed.
So it's not like an angular speed. And we'll come back to that probably Thursday. But so no, this is for the sun at its radius from the center of the galaxy is moving at 220 kilometers a second, give or take a few. And again, that's the rotational velocity around the center. So it orbits with a period of, I want to say 220 million years, but I'll check that number when I get to the slide. Don't write that down yet. Okay, so let's talk about some of the objects we find in the Milky Way. We said what we're doing is going from stars and the ISM to building up the pieces of the Milky Way. So we can't jump to this picture yet and explain all of it, but wanted to keep that in the back of your mind. So we need to talk about first clusters of stars. That's sort of the next size scale up. What are how do stars arrange themselves? Make sure I'm not skipping anything. So there are two types of star clusters. Open clusters and globular clusters. So I have a slide that's going to say all these facts in a few minutes, but let me write them down because I hate trying to copy stuff off a slide. So open clusters. In the Milky Way, there are about 1,000 of them. They typically have 20 to 1,000 stars in them. So 20 is actually not that big a number of stars. Even 1,000 isn't that big. These are fairly sparse. They have young stars. In particular, those O and B stars that live for a very, very short period of time. They're found in open clusters. You find them in spiral arms. So I didn't say where the spiral arms are, but you've probably all seen pictures of other galaxies with these grand spirals. So we think the Milky Way is a spiral galaxy, and this disk has spiral arms in it. And again, we'll come back to how exactly we know that. But when you look for open clusters, you find them in the spiral arms. So you imagine the disk filled with this sort of ninja star. There are the spiral arms, and then there's outside the spiral arms. The open clusters are firmly inside what we think of as spiral arms. And this is in fairly big contrast to the globular clusters. There's only about 150 known globular clusters. They have typically 10 to 100,000 stars. And they happen to all be old stars. And finally, you find them in the halo of the Milky Way, as opposed to the disk. So, not a big fan of just throwing all these facts at you, but it's sort of the best way to start doing this. But let's see some pictures of these things. So this is a popular T-shirt Joss insisted I show. If you imagine the Milky Way as a spiral galaxy, we are not in the center of it. He also liked this other depiction of the Milky Way, that, there are these, you can see these spiral arms laid out as subway tracks, and a lot of the familiar things are marked on it. You can see up there, it's not even a transfer station, it's the sun out in this crummy little red spiral arm. So it's really not all that important a place in the galaxy. That said, so let's take a look at some of these clusters. This is a typical example of an open cluster. As I said, 20 to 1,000 stars, kind of sparse, kind of pretty. Lots of stars of different colors. There are red stars, there are blue stars. So there are these young blue stars dominating most of the light, though. Here's a famous open cluster. This one's a little older than most of them, but this is actually, for those of you who don't know, the Pleiades, visible in the night sky. You can actually see these 7 stars with your naked eye. 7 takes a clear sky. You can probably make out 6 from Berkeley. That one in the upper right is tough to see. And of course, Josh gets money if I show you where this logo comes from, so I have to do that. And so here's, some of the facts I put up. I said there'd be a slide showing them again, but even worse than copying from a board, I think, is copying from a slide. So here are the 2 depictions of the different types of globular clusters. This open cluster with a couple hundred stars in it, maybe, and this globular cluster with 10,000 to, this is one of the bigger ones, 100,000 stars in it. And you see the colors are really quite different. The young stars are these O and B stars. They're very, very bright. They're very, very short-lived, and they dominate the color. So these open clusters of new star formation look blue, whereas these old globular clusters look quite red. And so we ask, can we be a little more quantitative about the ages of clusters? And so we have this main sequence turnoff technique. So if we make the assumption that all the stars in the cluster were born at about the same time, which isn't a terrible assumption, because once an O star is born, as we saw in the H2 region, it starts blowing out this wind, it ionizes the gas, it basically destroys the material the stars were forming out of, because stars form out of cold, dense molecular gas. Having a big, bright star in there, blowing a bubble, destroys any chance of future star formation, and then once it goes supernova, the cluster is basically done. So saying they're about the same age is not a terrible approximation. So if we see these plots of the main sequence going down in age, the early, very, very young, even the low mass stars haven't fallen onto the main sequence yet. They're still forming. Then there's some evolution. Most everything is on the main sequence. Some of the really, really bright stars have turned off, gone to the giant phase and moved off the main sequence. And then quite a bit later, some of the stars have gone supernova or nova and are white dwarf. There's a large portion of stars on the giant branches. And just the really low mass stars are left on the main sequence. And the super low mass stars stay in the main sequence longer than the age of the universe. So they're going to be there for a long, long time. Yes, question?
Why don't the old globular clusters get populated by new stars and the old ones supernova?
So it's a very interesting question. People are still looking into this, but basically it seems they have no gas in them. Somehow all this gas that formed in the first stars has been ejected from the system, or it's been used up. There's no material for forming new stars anymore. So we think a good but not really super well proven explanation is that the supernova of the first stars blow all the gas out of the system and just can't make any more stars if you don't have any gas. But so we can figure out sort of where these clusters are with regard to age by looking for this turnoff point. Because if they all formed at the same time, then knowing exactly the spectral type of the star here, the spectral type tells you, basically what kind of star it is. We know pretty well how long every kind of star lives. So by finding where things are starting to leave the main sequence, you can get a better handle on the age. And for a long time, at least until maybe 10, 15 years ago, globular clusters were our best handle on the age of the universe. They had turnoffs suggesting they were at least 13 billion years old. So we knew the universe had to at least be that old. It would be really weird to have something older than the universe in the universe. So people used to talk about globular clusters for aging the universe. Any questions about clusters? Yes?
I'm actually confused as to how, besides having more stars, how structurally they differ.
So yeah, that's a good question. Let's go back and look. Globular clusters have the name because they're these very spherical objects. They've been around for a long, long time. The interactions of all the stars have basically spherized themselves, and they're still gravitationally bound to each other. They're not going to disrupt. They're not going to float apart. Whereas a lot of open clusters are very loosely bound at best. And so over time, they basically drift apart. So we think the sun was formed in an open cluster, that most stars are formed in a cluster. That this gas cloud collapsed, lots of stars were formed, and then the O and B stars blew up, disrupted the cluster, and it's gone. So these stars, once they lose the gas, they lose their gravitational glue in a sense and all drift apart. So finding open clusters is hard. They don't last for very long, and they really will drift apart in a short amount of time. That's why we said this Pleiades picture, this is kind of already a disrupted cluster. We don't think there's enough mass here anymore for these stars to all be gravitationally bound to each other, and they'll just drift apart over time. But it's an interesting question, and what exactly globular clusters are is still a very hotly debated topic of research. Some people think they're other galaxies that have fallen into the Milky Way, whereas other people think they're supermassive open clusters that over time have drifted out of the disk up into the halo. But the fact that we only find globulars right now in the halo, we only find open clusters in the disk, suggests that there really is a difference between the two, that all the star formation is going on in the disk. And somehow these big balls of old stars have gotten out into the halo. Whether they fell in or drifted out is still an open question. Any other questions on clusters? And I should say that we make the assumption clusters are useful because they're stars we think have formed at the same time. They're all roughly about the same distance apart. The distance between the stars is much less than the distance from us to the cluster. And we usually assume they're all the same chemical composition because they formed out of the same gas. Although if any of you went to the first colloquium of the semester by Charlie Conroy, people are starting to call a lot of those assumptions into question too. So they may not be as simple systems as we would like. So let's put that up. So talking about these two different kinds of clusters, it sort of hints that there may be different kinds of stars in the Milky Way. That if the stars in the globular clusters came from a different place than the stars from the open clusters, then maybe even outside of clusters there are different populations of stars. So let me cover this one up and talk about, in general, stellar populations. And so this is some astro jargon. I'll try and make it clear. So in general, we talk about two populations of stars. We call them Pop 1 and Pop 2, creatively enough. So let's talk about population 1 stars. These are stars found in the disk, again, in the site of star formation. They're on roughly circular orbits, just like the sun, roughly going around the galactic center. So they have an age of between 0 and 10 billion years. So again, the disk is where the new stars are being formed. So the new stars are population 1 stars. But there's also a reasonably old population, going back to about 10 billion years, of population 1 stars. And the big thing that distinguishes them from population 2, which we'll get to in a second, is what we call their metallicity. I think that has 2 L's. So again, recall that astronomers refer to everything heavier than helium as a metal. But typically, to actually get a quantitative measure of metallicity, we measure this ratio. The abundance of iron to the abundance of hydrogen in the star. So how much iron is in this star? And we're talking about, for stars, the surfaces. So we're not concerned about the iron that's being created in nuclear fusion at the center. We hope that the surfaces of the stars are undisturbed enough that the metallicity, this ratio that we observe in spectral lines from the surface, is representative of the gas that the star is formed out of. And we can make this a little more quantitative. Of course, we do everything on a log scale because we're astronomers. And it's the log because we're doing logs, we have to take it as a ratio of something. We need a 0 point. Same problem we had with magnitudes. So we set the 0 point here to be the metallicity of the sun, this iron to hydrogen ratio measured in the sun itself. So what would be the metallicity of the sun on this scale then? I hear 1, I hear 0. So it's the sun over the sun is 1. The log of 1 is 0. And I'm writing approximately 0 because I'm talking about now all Pop 1 stars. Pop 1 stars are generally solar metallicity. So their metallicity is typically about 0. So by definition, essentially, the sun is a Pop 1 star. So let's talk about Pop 2. These stars are in the halo as opposed to the disk. They're about 10 billion years old, maybe older. And most importantly, they're what we call metal poor. So their Fe over H ratio goes from -1 to -2. So on a log scale, that's 10 to 100 times less iron than the sun. And if any of you went to Anna Frabel's colloquium the other week, she was talking about the most metal-poor stars. So currently, the record holder for this ratio is -5.4. So that's over almost 1 million times less iron to hydrogen than the sun has. But typical POP2 stars have this fairly low metallicity ratio. So this makes you ask about the origin of these stars. Where did they come from? And the general picture we have is that these older, more metal-poor stars formed first from sort of a gas without much metals in it. Then through stellar nucleosynthesis, through supernova, through planetary nebula, they basically form these heavier elements, put them back into the interstellar medium, and then the POP1 stars form out of that, having a larger amount of metals. And so this, makes you ask, well, what about the first stars in the universe? So I don't want to spend much time on this, but this is kind of what I work on. So there's a theoretical population of POP3 stars. Again, this is purely theoretical. These would be quote-unquote metal-free. Because when we talk about the Big Bang, we'll say that we believe the Big Bang only produces essentially hydrogen and helium and maybe a tiny bit of lithium, but really nothing else. So there should be 0 iron in these stars. These are essentially the first stars in the universe. And hypothetically, we expect them to have formed about 300 million years after the Big Bang. And we expect them to be very short-lived, explode very quickly, and POP2 stars formed very quickly afterwards. So again, I'll stress there is absolutely no observational evidence for POP3 stars. But we kind of have to believe they exist, that something had to create the first metals that wound up in these old POP2 stars. Okay, so are there any questions about these populations? Well, let me say one more thing. I mentioned this was jargon because this can be confusing. POP1 is the newest. POP2 is old, and POP3 is the oldest. So depending on how you think, this may be slightly counterintuitive. You'd want the first population to be the oldest, but no, it's the newest. Because astronomers have this habit of naming things before they actually know what they are. All right, any questions on stellar populations? Yes?
The POP2, you say they're in the halo, so are they also all in globular clusters?
So no, that's a very good point, and I forgot to mention that. Thank you. I said these are roughly on circular orbits. These are sort of in wildly erratic plunging orbits. So they're not just orbiting like the disk. They can be up here and will go down here and come back. And so they really fill the spherical halo. So, but yes, I mean, the stars in open clusters are basically, by definition, all POP1 stars, and the stars that are in globular clusters are all POP2 stars. But there are, as I said, there's only about 100, 150 globular clusters. There are lots of POP2 stars not in these clusters, and because open clusters don't stay around for very long, there's lots and lots of POP1 stars, for example, the sun, that isn't in a cluster. Yeah, good point. They really fill the sphericalness of the halo. Yes?
How do the globular clusters move in the galaxy?
They are also kind of on these erratic orbits. Michael.
So in a galaxy that doesn't have this disk-like shape, do we still use these populations?
So when we talk about other galaxies, we'll go over that. But generally, the metallicity is the key distinguishing feature. Pop 1 stars are about solar metallicity, and Pop 2 stars are more metal poor. Okay, so let me show a few more slides on the Milky Way, and then we'll, in the remaining time, talk about how we figure out the structure of the Milky Way as a whole, how we actually know all these facts I just sort of threw up on the board. So again, here's the sort of summary of what I said. In the halo, we have and the globular clusters, we have these old metal poor stars that's basically spherical. It has no gas and dust. Whereas the disk is where the young stars live. There are star-forming regions and H2 regions. There's the emission nebulae, there's gas, there's dust. There's a lot going on in the disk. And then, I didn't talk too much about it, surrounding the galactic center is this bulge. And the bulge has both Pop 1 and Pop 2 stars. It's kind of redder because it has a lot of old stars, but it has some new star formation too. So here's some better pictures of the Milky Way than I could possibly draw. This is kind of a face-on view. As I said, we think the Milky Way is a spiral galaxy with these spiral arms. It is all gravitationally bound, and we think there are about 200 billion stars in the Milky Way. Here's a side-on view, and this is one point that we should make clear. Completely unlike my drawing, the disk is very, very thin. Sort of the aspect ratio of the Milky Way. It's about a DVD. It really is a very, very thin disk. Again, with the bulge sticking out of the middle, but the disk itself, compared to how long it is very, very thin. 1,000 light years to 100,000 light years in the terrible units of light years. And the sun is kind of about halfway out in this picture. And so the sun orbits, 2 times 10 to the 8, 250 million year circular orbit around the center of the galaxy. And we should also mention that although the disk is thin, the sun does kind of oscillate up and down in the disk. And that is another period of about 65 million years. But so the sun moves through the galaxy over time. And that's an interesting point to come back to. Okay, I don't know why Josh put that in there, but he did. Okay, but let me say one other thing about how we can more quantitatively talk about the galaxy. We mentioned earlier the idea of a galactic coordinate system of L and B, where we define L of 0 to be, or L is the coordinate in the disk, sort of an angle, and L of 0 points at the galactic center, and then B is an angle off the disk. So you can kind of see in this picture, we've taken it at a time where the optical observable Milky Way from the Earth is roughly flat on the sky. This isn't how it looks everywhere. For those of you who have seen the Milky Way, most places you're going to go, it kind of arcs overhead. But in this picture, it's flat, and we can see that L of 0 is directly at the galactic center where this black hole lives. And then we have these angles in L as we go around the disk, and then these angles in B as we point off the disk. So galactic coordinates are nice because they don't change where the sun is or where the moon is or where the Earth is. It's all fixed to the galactic center. So yes, on this 225 million year period, we'll need to rethink galactic coordinates, but not in our lifetime. And then for some reason there are a lot of slides on this. Okay. All right, so any questions on that before I delve into things? Yes?
The distribution of the halo versus the disk, is the disk right in the middle of it?
The disk is basically cutting the halo in half, yeah.
Like at the equator.
Yeah. So the picture is sort of a DVD embedded in a sphere. And the DVD cuts across the equator. So we'll get back to that when we talk about dark matter, but not necessarily. Yes?
So do we not think we have a bar now?
So I didn't mention it. We do think the Milky Way is a barred spiral, but when we talk about evidence for spiral arms, we'll talk about sort of evidence for a bar in the middle of the galaxy. So for those of you who don't know, half the galaxies we look at, instead of having a round bulge, kind of have a bar in which the spiral arms come off of. And we do think the Milky Way has a bar. Yes?
How far is the halo?
How far is it? So I said the radius of the disk in stars is about 25 kiloparsecs. That's about the furthest stars you see in the halo, too. So sort of a sphere with radius 25 kiloparsecs. Okay, so I've got a little short on time, but hopefully I can get through a little bit of this and then leave the rest to Josh. Start talking about how do we know all this? What are some ways we can probe the structure of the Milky Way itself? Before I do that, let me say one quick thing. So this galactic coordinate of L and B is a celestial sphere coordinate in the sense that it tells us as observers on the Earth where to look for an object. That's why it only has two coordinates, because we only need angles. Everything is basically the same distance away on this sphere we imagine surrounding us. To actually talk about where things are in the galaxy, we need a third coordinate. So we can use galactic coordinates L and B and add R, where R is basically the distance from the sun. Other people will talk about this in cylindrical coordinates, where R will be the distance from the center. You'll have a theta angle around the disk, and then you'll have a Z for height off the disk. But I'm not going to go into too much detail there. Just know that you need a third coordinate to actually talk about positions.
We can put zeta equals 0 for the sun.
Again, it's convention. So yeah, towards the sun is a good choice. I don't actually know anyone who uses that coordinate system. All right, so we're going to say in the next 10 minutes, start talking about how do we know this? So I think this is more interesting than just rambling off a list of facts, actually talking about where some of these come from. So let's start with the very simplest thing. Let's count stars. So again, using those coordinates I just mentioned, R, theta, Z, let's not worry too much about where they're actually pointing. I want to know, in the Milky Way, the number of stars per cubic parsec. Sort of give me a census of the density of stars as a function of position in the galaxy. That is essentially what we mean when we talk about the structure of the galaxy. So I'm going to say there's a better way to do this. To instead count dn d mass, so the number of stars per mass interval. Can anyone think of why this is a better way to do this? So basically a star's mass determines all of its properties. So if I want to compare apples to apples, I need to do it per mass interval. I want to know the number of O stars per cubic parsec, the number of B stars per cubic parsec, because they're not necessarily the same thing. They live for different ages. So M stars, for example, if they're drifting out of the disk, there will be M stars out of the disk because they live long enough to do that, but O stars don't. And so this also determines their flux. So the stars are going to get fainter the further away they go. So if I don't have a well-defined sample, it's hard to tell the difference between a faint star nearby and a bright star far away. So if I'm going to go by spectral type, I'm going to find all the O5 stars and do them. I'm going to find all the O4 stars, et cetera, et cetera. So, but in principle, this is simple enough. We're going to count stars, and we're going to measure the distance to them. So let's recall. The distance modulus between the apparent magnitude of a star and the absolute magnitude of a star. So if we have a fixed spectral type or a fixed mass, we know what m is. Look it up in the back of Carolyn Ostley. This is measured. We need, however, to separate their distance and their extinction. So there's some convenient ways that if we have a spectra, we can measure the reddening. And we didn't mention, but the reddening is related to the extinction, so we can go back to the overall extinction. And so these are, in principle, disentangleable. So let's do a quick example, and this I'll probably have to stop after this. But if we take a G2 star, so this is a solar type star. The sun is a G2 star. And we measure its V-band apparent magnitude to be 11, and its parallax to be 0.01 arc seconds. I'll say, we'll put this up briefly, but I'll write it again. Parallax in arc seconds is equal to 1 over the distance in parsecs. So this parallax implies what distance for the star? So this is 0.01 arc seconds. So 100 parsecs. And because I said this is a G2 star, we figured out, based on the spectra, we looked at all the absorption lines, we know this is a star like the sun. Then we know its absolute magnitude. Make that big. Is 4.7. That's just, we know the star is like the sun, so we know what its absolute magnitude has to be. So we can solve for the absorption from that formula. Just do some algebra, plug in the numbers. The 100 is the distance in parsecs. So this star has 1.3 magnitudes of absorption. That's what you get plugging in all these numbers. And if we remember, so the actual flux, this is a log, we need to exponentiate this. This exponent comes from just the conventions of that 2.5, etc. in magnitudes. It's a factor of 3.3. 3.3 times less flux than we would expect to see this star if there were no dust. So we can set, on average, this is a good rule to know. In the Milky Way, there's about 1 magnitude of extinction for something 1 kiloparsec away. So this is a general rule of thumb. This depends heavily on what line of sight you're looking on, i.e. on L and B. For example, if we're looking out of the disk, there will be less extinction than in the disk, because we said all the dust lives in the disk. If we look towards the galactic center or out of the galactic center, we see different amounts of dust. But as a general rule of thumb, a star a kiloparsec away has a magnitude of extinction. So let me define one other term for you, because I have a minute and it seems like a good thing to do. And I'll let Josh take over on how we actually count stars, but I want to talk about solid angle. So for those of you who don't know, when we talk about counting things on the sky, we need to talk about what fraction of the sky we're actually looking at. So we need, like we have 360 degrees in a circle, we need some 2D angle on the sky. So we typically define this as a steradian is our unit of solid angle. And we define that there are 4 pi steradians on the entire sky. So again, think of this as sort of a square of angle. For example, a square degree is a square 1 degree on a side. So let's convert this, just so you have an idea, into degrees. So this is, I should say, a steradian is a solid angle radian. So it's 1 radian on a side. So if we take 4 pi and multiply by our usual conversion factor of 180 degrees over pi degrees per radian, we need 2 of these because this is solid angle. It's a radian on a side. Not a very nice number. Yes, question. So, by convention, no. Yeah. It is 4 pi steradians on the sky. I think the way to think of it is when you're doing these sort of angular integrals, you have your 2 angle directions. One you integrate from 0 to 2 pi. The other only needs to go from minus pi over 2 to pi over 2. That otherwise you start double counting angles. I think that's where it comes from. That if you do, that's right. If you do the integral over solid angle, which we're saying if we integrate over the whole sky, this is 4 pi. If you break this up into, if you remember from spherical coordinates, we're leaving out r, but this is sine theta, d phi, not just the product of d theta and d phi. If those of you who haven't seen this kind of integral before, don't worry about it. But that's where the extra factor of pi goes, that we have this sine theta term. So there are 4 pi steradians on the sky, and it works out to be a little over 40,000 square degrees. All right, so I'll leave the rest for Thursday.